minus 235 degrees Celsius. That is the temperature of the ice beneath your boots if you were standing on Sputnik Planitia today. Nitrogen should be rock at that temperature, inert, motionless, dead for 1 billion years. And yet, on the surface of the coldest, driest world New Horizons ever photographed, something has been moving, not once, recently. What is dragging streaks of liquid across a glacier where liquid should not exist? What is the molecule sitting on Pluto's ice that no laboratory on Earth has ever seen before, and that matches nothing in 90 years of spectroscopy? And why, 4 billion kilometers from the Sun, is a moon slowly turning red because its parent world is exhaling onto it? I want to be honest with you before we go further. When the first of these papers landed in my feed, I assumed it was a data artifact, a modelling error, something a peer reviewer would catch and quietly correct. It wasn't. The James Webb Space Telescope, working in concert with data New Horizons carried home a decade ago, is now describing a Pluto that should not behave the way it behaves. A world with a working thermostat, a moon that steals part of its atmosphere, and a surface chemistry that has stumped some of the best-equipped spectroscopists alive. This is the story of how a demoted, disrespected dwarf planet on the ragged edge of the solar system became one of the strangest active worlds we know of. Not because it's warm, not because it's alive, in any sense we currently understand that word, but because at minus 235 degrees, physics is still finding ways to surprise us. On the 18th of February 1930, a 24-year-old farm boy from Kansas named Clyde Tombaugh sat alone in a cold observatory dome in Flagstaff, Arizona, comparing two photographic plates of the night sky taken 6 days apart, hunting for a single point of light that had moved against the fixed stars behind it. He found it. The object was so faint that most professional astronomers of the era would have dismissed the shift as an instrument flaw, a scratch on the glass, a trick of the eye after too many hours at the blink comparator. Tombaugh did not dismiss it. He had spent months working through a systematic search of the ecliptic that most people would have abandoned out of sheer tedium, and on that February afternoon he became the first human being in history to lay eyes on Pluto. For 76 years, Pluto occupied a strange emotional space in the public imagination. The ninth planet, the runt of the solar system, a name chosen by an 11-year-old English schoolgirl named Venetia Burney because it evoked the Roman god of the cold, dark underworld. Then, on the 24th of August 2006, delegates at the International Astronomical Union's General Assembly in Prague voted to redefine what a planet actually is, and Pluto, unable to clear its orbital neighbourhood of debris the way Jupiter or Earth does, was reclassified as a dwarf planet. The backlash was immediate, emotional, and in some quarters permanent. Alan Stern, the planetary scientist who would go on to lead the mission that finally visited Pluto up close, has never stopped objecting to that vote, and I find myself, more often than not, on his side of the argument, because here is the thing that gets lost in the taxonomy debate. Whatever label you attach to it, Pluto sits roughly 5.9 billion kilometers from the Sun on average, tracing an elongated 248-year orbit that carries it as close as 29.7 astronomical units and as far as 49.3 astronomical units from the star that barely warms it at all. Sunlight that reaches Pluto's surface arrives roughly 1,600 times fainter than it does on Earth, bright enough to cast a shadow, dim enough that if you stood on the ice and looked up, the Sun would appear as little more than an intensely brilliant star. The surface temperature swings between about minus 240 and minus 218 degrees Celsius, cold enough that nitrogen, the gas that makes up most of the air you are breathing right now, exists there as solid ice, as bedrock, as glaciers hundreds of meters thick. For decades, the working assumption among planetary scientists was straightforward, almost boring. A world this small, this cold, this far from any source of internal heat, should be geologically dead. No plate tectonics, no volcanism, no weather worth the name. Just a frozen, cratered relic, pristine because nothing had disturbed it since the solar system's formation 4.5 billion years ago. That assumption survived essentially unchallenged until the 14th of July 2015, when a spacecraft the size of a grand piano, travelling faster than any object ever launched from Earth, swept past Pluto at a distance of just 12,472 kilometres and began sending home images that took the entire field of planetary science by surprise. New Horizons had been a decade in the making by the time it reached Pluto, launched on the 19th of January 2006, atop an Atlas V rocket, accelerating to roughly 58,536 kilometers per hour relative to Earth, fast enough to make the 4.5-hour drive from New York to Los Angeles take about 6 minutes, if such a thing were possible on a highway. Tucked inside the spacecraft was a small aluminum canister containing an ounce of Clyde Tombaug's cremated remains, a detail I find genuinely moving every time I think about it. A farm boy who spent a winter squinting at photographic plates, riding along on the mission that would finally show humanity the world he found. It took New Horizons 9.5 years to cross the 4.67 billion kilometers separating Earth from its target, and when it finally arrived, the images beamed back, delayed by more than 4 hours simply because of the time it takes light, and therefore radio signal, to cross that distance, revealed a world nobody had predicted. Instead of a dead, uniformly cratered ball of ice, New Horizons found mountains of solid water ice rising 3.5 kilometers into a hazy nitrogen sky. It found a heart-shaped region later named Tombaugh Regio, dominated by a smooth, crater-free plain of frozen nitrogen roughly the size of Texas and Oklahoma combined, later christened Sputnik Planitia. It found evidence of geological activity so recent, less than 10 million years old by some estimates, and in places likely far younger, that Pluto had to be doing something to generate or retain internal heat, something nobody had built into the models. Sputnik Planitia, in particular, showed a pattern of polygonal cells, each one 30 to 40 kilometers across, that mirrored the convection patterns you'd see in a pot of simmering water. Except this pot was made of nitrogen ice, hundreds of degrees below anything a stovetop could produce, and yet it was turning over, slowly, methodically, like a planet-scale lava lamp running on almost nothing. I remember reading the first New Horizons science summaries and feeling something close to vertigo, the sense that an entire category of worlds, the small, cold, supposedly boring ones, had just been quietly rewritten. If Pluto could do this on a fraction of the internal heat budget available to Earth, what were we missing about every other small icy body scattered across the outer solar system? That question, as it turns out, would not get fully answered by New Horizons alone. The spacecraft did what a flyby can do. It took a single extraordinary snapshot and then kept flying, eventually passing the Kuiper Belt object Arrokoth on New Year's Day 2019, and continuing outward, its instruments still transmitting data back across a gap that keeps widening every second. What New Horizons could not do was watch Pluto change over time. A single flyby captures one season, one moment, frozen in the data the way an old photograph freezes a face. And Pluto, with its 248-year orbit and its dramatically shifting distance from the Sun, is a world defined by seasonal change on a timescale that dwarfs a human lifetime. To understand whether what New Horizons saw was a snapshot of something permanent or something transient, scientists needed a second set of eyes, one capable of studying Pluto not for a matter of hours during a single flyby, but repeatedly, patiently, from a fixed vantage point nearly 1.5 million kilometers from Earth. That second set of eyes launched on Christmas Day, 2021. Its name is the James Webb Space Telescope, and what it found when it finally turned its mirrors toward that tiny, distant world would take almost everyone by surprise all over again, because here is the uncomfortable truth this story keeps circling back to. We thought we understood Pluto once we'd seen it up close. We had the photographs, we had the maps, we assumed the mystery was mostly solved, filed away, ready for the textbooks. What Webb was about to show us is that seeing a world clearly, even once, even spectacularly, is not the same thing as understanding how it works. And the gap between those two things, between seeing and understanding, is exactly where this story lives. every atmosphere in the solar system that we understood before 2025 played by roughly the same rules. Gas molecules absorb and re-radiate energy according to well-established physics. Heat moves from warm regions to cold ones, and the overall energy budget of a planet's air can be modelled with tools that have worked reliably for Venus, for Mars, for Jupiter, for Earth itself. Pluto's atmosphere, composed of roughly 99% nitrogen, with faint traces of methane and carbon monoxide, is almost absurdly thin by comparison. Its surface pressure hovers around 1 Pascal, something on the order of 100,000th of what you're feeling on your skin right now, reading this. An atmosphere that thin should behave like a rounding error, a negligible smudge of gas too sparse to meaningfully regulate anything. That was the assumption, and it was wrong. In 2017, a planetary scientist named Shi Zhang, then working through the aftermath of the New Horizons data at UC Santa Cruz, published a paper that struck most of his colleagues as, in his own words, a crazy idea. Zhang proposed that Pluto's atmosphere wasn't behaving like a simple gas envelope at all. It was being dominated by haze. Not the vague cosmetic haze you might picture drifting over a city skyline, but a structured, layered system of microscopic particles formed when ultraviolet sunlight breaks apart methane and nitrogen molecules high in Pluto's atmosphere, triggering a photochemical cascade that builds up complex hydrocarbon particles, the way smog forms above a highway, except here the particles fall gently downward through hundreds of kilometers of near vacuum, layer after layer, like sediment settling through still water. Zhang's proposal went further than simply noting the haze existed. He argued that these haze particles, heating up when they absorbed sunlight and cooling rapidly by radiating in the mid-infrared, were actually controlling the entire energy balance of Pluto's atmosphere, not the gas. The haze, an idea that inverted the standard model for how a planetary atmosphere works. Here's why that mattered so much to the people who first heard it. If Zhang was right, Pluto's atmosphere didn't just happen to have haze in it, the way Earth's atmosphere happens to have clouds. The haze was in effect running the thermostat. And Zhang made a testable prediction in that 2017 paper, the kind of specific, falsifiable claim that either makes a scientist's career or quietly buries it in the footnotes of history. If the haze was truly cooling Pluto's atmosphere the way he described, it should be radiating measurable heat in the mid-infrared range, a signal that no telescope operating at the time had the sensitivity to detect. He would have to wait 4 years, as it turned out, until a telescope capable of testing his idea even reached orbit. That telescope arrived at the second Lagrange point, roughly 1.5 million kilometers from Earth in early 2022, unfolded its 18-segment gold-coated mirror and began the long, patient work of commissioning its instruments before turning toward its first scientific targets. Pluto was not first on anyone's priority list. The early Webb headlines belonged to galaxies at the edge of the observable universe, to exoplanet atmospheres, to the shimmering geometry of Neptune's rings. But eventually, astronomers pointed the mid-infrared instrument, MIRI, toward that tiny world in the Kuiper Belt, and in May 2023, they captured something no previous instrument had ever managed: a high-resolution mid-infrared spectrum of Pluto spanning wavelengths from 4.9 to 27 micrometers, a slice of the electromagnetic spectrum that earlier telescopes simply lack the sensitivity to explore in any useful detail. The results, published across a series of papers through the spring of 2025 and culminating in a study in Nature Astronomy on the 2nd of June that year, confirmed Zhang's 8-year-old prediction almost exactly. The haze particles in Pluto's atmosphere were indeed radiating strong thermal emission in the mid-infrared, precisely the signature Zhang had said should exist if his model was correct. "We were really proud," Zhang told researchers documenting the discovery, "because it confirmed our prediction. In planetary science, it's not common to have a hypothesis confirmed so quickly." I want to sit with that phrase for a moment. Quickly, in Zhang's telling, meant 8 years. 8 years of a colleague quietly holding on to an idea that most of the field considered implausible, waiting for the instrument that could finally prove him right. There's something in that patience I find difficult not to admire. But confirming the mechanism only deepened the mystery it was meant to resolve, because once researchers accepted that haze, not gas, was regulating Pluto's atmospheric temperature, an entirely new question opened up beneath their feet. What does an atmosphere that thin, with a thermostat running on suspended smog particles instead of bulk gas, actually do to the world beneath it over the course of a Plutonian year? The MIRI instrument didn't just capture a single spectrum, it also gathered light curves, repeated brightness measurements at 18, 21 and 25 micrometers, tracking how Pluto's thermal emission changed as the dwarf planet rotated on its 6.4-day axis. Comparing those light curves against detailed thermal models let the research team, led by Tanguy Bertrand and Emmanuel Lelouch, place real numerical constraints on properties that had previously been little more than educated guesses. The thermal inertia of different surface regions, meaning how quickly or slowly a patch of Pluto's crust heats up and cools down, the emissivity of the ice, the actual temperature of specific terrains as they rotated in and out of sunlight. And what those numbers revealed was a world engaged in a slow seasonal redistribution of its own substance on a scale that made the phrase geologically dead feel almost embarrassing in retrospect. As Pluto swings through its 248-year orbit, different regions of the surface take turns facing the sun more directly, and the volatile ices, nitrogen, methane, carbon monoxide, respond by sublimating in one location and refreezing in another, an entire hemisphere's worth of frozen atmosphere quite literally picking itself up and migrating across the planet over the course of decades. Sputnik Planitia, sitting near Pluto's equator, acts as the dominant reservoir feeding this cycle, its nitrogen ice cycling between solid and vapor as the seasons turn, thickening in some epochs and thinning in others, driven by an energy budget that depends critically on how much sunlight the haze layer above it is absorbing and re-radiating at any given moment. Here is where the forward pull becomes impossible to ignore. If Pluto's haze genuinely controls its atmosphere's energy balance the way Zhang predicted and Webb confirmed, then the world's climate, its ice ages, if you want to call them that, its patterns of freezing and thawing across the surface, is being dictated by microscopic smog particles suspended in an atmosphere thinner than the air at the edge of Earth's exosphere. Zhang himself pointed toward the implication that keeps this story from staying contained to one small world at the edge of the solar system. Neptune's moon Triton and Saturn's moon Titan both host similar nitrogen and hydrocarbon atmospheres thick with haze, meaning the physics discovered on Pluto might apply across an entire class of worlds we thought we already understood. We need to rethink their roles too, Zhang said, and that single sentence, quiet as it sounds, amounts to reopening the books on atmospheric science for every hazy nitrogen world in the outer solar system. But there was a second thread buried in that same set of 2025 papers, one that troubled the picture even further, because if Pluto's haze was busy regulating an entire planet's thermal balance, something equally strange was happening to where that haze, and the gases feeding it, eventually ended up. Some of it, it turns out, wasn't staying on Pluto at all. Some of it was leaving, drifting outward across empty space, and settling onto the surface of another world entirely. That is where the simple, tidy story of Pluto has an unusual atmosphere stops being simple and starts becoming something far stranger. Charon should not have a colour problem. By every reasonable expectation built from decades of outer solar system observation, Pluto's largest moon ought to be a relatively unremarkable ball of water ice, roughly 212 kilometres across, just over half of Pluto's own 2,377 kilometre diameter, making the pair close enough in size that some scientists have long argued they constitute a binary system rather than a planet and moon pair in the conventional sense. Charon has no atmosphere of its own, essentially no seasonal ice migration, no photochemical haze factory turning sunlight into smog. Its surface, dominated by water ice mixed with ammonia-bearing compounds, should be geologically simple, chemically quiet, and more or less uniform in colour across its face, except for two regions, roughly at its north and south poles, where the ice turns a deep, unmistakable red, a stain later given the almost theatrically fitting name Mauda Macula. For years after New Horizons returned its images in 2015, the leading explanation for Mauda Macula sounded almost too elegant to be true, which should have been the first warning sign that reality would turn out messier. The proposed mechanism went like this. Pluto's atmosphere is constantly, if slowly, leaking methane molecules into space, a process driven by the combination of low gravity. Pluto's surface gravity sits at roughly 6% of Earth's, and the relentless erosion of solar ultraviolet radiation stripping gas from the upper atmosphere, some fraction of that escaping methane, rather than drifting off into interplanetary space entirely, ends up captured by Charon's gravity instead, falling onto the Moon's polar regions during the decades-long stretches of Charon's own extreme seasons, when those poles are plunged into total darkness and temperatures crash low enough for methane to freeze directly onto the ice. Once trapped there, exposed to cosmic rays and solar ultraviolet light, even during the long polar night, the frozen methane undergoes a slow chemical transformation into tholins, complex reddish-brown organic compounds, the same broad family of molecules responsible for the ruddy tint on Titan's dunes and the reddish hues scattered across Kuiper Belt objects throughout the outer solar system. Methane leaves one world, gets captured by its neighbour, and gets cooked by radiation into a visible permanent stain, tidy, testable, satisfying, and that is roughly where the story sat for nearly a decade, a plausible, elegant hypothesis repeated in documentaries and textbooks, treated as settled enough to move past. This is, I think, one of the more instructive moments in this entire investigation, because it shows how a genuinely reasonable scientific explanation can survive for years, not because every detail has been confirmed, but because nobody yet has the instrument sensitive enough to check the fine print. The fine print, in this case, turned out to matter enormously. When the James Webb Space Telescope's MIRI instrument began capturing separate mid-infrared light curves for Pluto and Charon in the early 2020s, something no previous telescope had been able to do, since older instruments simply couldn't resolve the two bodies distinctly enough to measure their thermal emission independently. Researchers finally had the tool needed to test the methane transfer hypothesis against hard numbers rather than plausible narrative. What they found complicated the tidy story considerably. Linfeng Wan, then a doctoral student working under Shi Zhang, had published a 2023 study predicting the specific amplitude of Charon's rotational light curve, essentially how much Charon's thermal brightness should swing up and down as it rotates, if the methane capture and irradiation model was accurate, and the resulting surface deposits had the properties the model assumed. When Webb's actual light curve data came back, and researchers compared it against Wan's prediction, the agreement was close, a genuine confirmation, and by any measure a scientific win worth celebrating. But close agreement on light curve amplitude is not the same thing as a complete explanation, and the very act of gathering this precise new data opened up questions the original 2015-era hypothesis had never been forced to answer. How much methane precisely is Pluto losing to space at any given point in its 248-year orbit? And does that rate change enough across the seasons to explain the specific intensity of Mauda Macula's redness? The old models, built on comparatively crude estimates of atmospheric escape, hadn't been tested against detailed thermal inertia measurements of Charon's actual polar surface, measurements that only became possible once Webb's light curves let scientists back out real physical properties, not just modelled ones, for the ice at Charon's poles. And when those thermal inertia values came back, they forced a re-evaluation of exactly how efficiently methane sticks, freezes, and accumulates at Charon's poles versus how much simply bounces off a surface too warm, even in polar darkness, to hold on to it. A detail one of the scientists working the problem summarised bluntly. For most of Charon's surface, methane molecules arriving from Pluto's atmosphere just bounce off and re-emit back into space, and only in the narrow window of extreme cold at the deep poles does enough of it stay behind long enough to be irradiated into the tholins that paint Mordor macula red. That distinction matters more than it might sound. It means the red staining on Charon isn't a simple, steady drizzle of methane raining down evenly across the moon's polar caps. It's a tightly constrained seasonal bottleneck, a narrow thermal window that opens and closes as Charon's own 5.1-day rotation and Pluto-Charon's mutual 248-year orbital dance carry the poles through cycles of light and total darkness lasting decades at a stretch. Get the thermal inertia numbers wrong by even a modest margin, and the entire predicted intensity of Charon's red caps shifts, which is exactly why the Webb light curve data mattered so much. It wasn't confirming that the general mechanism existed. New Horizons had already made that case reasonably well in 2015. It was pinning down, for the first time, the actual physical parameters governing how efficiently the process runs, parameters that the original elegant hypothesis had simply assumed rather than measured. I find this detail, the bouncing methane, the narrow thermal window, the fact that an entire visible geological feature on a moon depends on a temperature threshold measured in single-digit Kelvin differences, to be one of the most quietly staggering pieces of this whole story, and it is worth pausing on it for a moment before we move forward. We are talking about one celestial body painting a visible mark onto another celestial body across open space, with no physical contact between them, using nothing but escaping gas and the accident of orbital mechanics positioning one world's polar cold trap in just the right place to catch what the other world exhales. Nowhere else in the solar system, as far as current observations extend, does one planetary body chemically stain another this way. Not Earth and the Moon, not Saturn and its rings of icy debris, which is a different physical process entirely. Not Jupiter and its 4 large moons, despite their far more violent electromagnetic and volcanic interactions. Pluto and Charon appear to be doing something genuinely singular, an interplanetary transfer of atmosphere resulting in a permanent, visible geological feature on a neighbouring world, and it took a space telescope built to study the birth of the first galaxies to finally measure the mechanism with any precision. But even this revised, more precisely measured picture of the Pluto-Charon methane exchange still left the researchers with an uncomfortable gap between prediction and observation, because thermal inertia measurements are proxies. They tell you how a surface responds to heating and cooling, but they don't directly tell you the full chemical inventory sitting on that surface, or whether the red material at Charon's poles is purely simple tholins built from methane alone, or something chemically richer, built from a wider menu of molecules escaping Pluto's atmosphere that nobody had previously accounted for. And that gap, that nagging sense that the light curves were measuring something real but incomplete, sent a related team of researchers back into Webb's spectroscopic data with a different question entirely. Not how much heat is Pluto's surface radiating, but what precisely is sitting on Pluto's ice in the first place, molecule by molecule, wavelength by wavelength. That question, it turns out, would lead somewhere far stranger than anyone on the team expected. Because buried in the spectrum Webb captured of Pluto's surface, and independently, in a spectrum of an entirely different world 800 million kilometers closer to the Sun, sat a signal that matched nothing in 90 years of laboratory spectroscopy. Not water ice, not carbon dioxide, not any of the tholins, hydrocarbons or nitrogen compounds catalogued across decades of outer solar system research. Something else, something that, as of this telling, still does not have a name. In late June of 2026, an international research team led by Bruno Bézard and Emmanuel Lelouch at the Paris Observatory published, first as a preprint, then accepted into the peer-reviewed journal Astronomy and Astrophysics, a discovery that, in the driest possible academic language, described an unidentified absorption feature at 11 micrometers on the surface of Titan and Pluto. I want to translate that sentence out of the language of spectroscopy and into something closer to what it actually means. because the plain English version is considerably more startling than the technical phrasing suggests. Somewhere on the frozen surfaces of two of the most thoroughly studied icy worlds in the solar system, there is a chemical compound absorbing infrared light at a very specific wavelength, and nobody, not the team that found it, not the wider community of planetary spectroscopists they consulted, not any existing laboratory database of ice and organic compound spectra, can say what that compound actually is. To understand why this matters, you need to understand, even briefly, how scientists read the chemical fingerprints of distant worlds in the first place. Every molecule, when struck by light, absorbs specific wavelengths corresponding to the exact ways its atoms can vibrate, stretch, and bend relative to one another, a physical signature as distinctive, in its own way, as a human fingerprint. Point a spectrometer at sunlight reflecting off a planet's surface or atmosphere, and you get back a spectrum riddled with dips, dark bands where specific wavelengths have been absorbed by whatever molecules happen to be present. Match those dips against a laboratory-measured catalogue of known substances, and in most cases, you can identify precisely what you're looking at without ever physically touching the object in question. It is, in a very real sense, chemistry conducted at a distance of billions of kilometres, and it has worked reliably enough, for long enough, that the entire field of remote planetary spectroscopy rests on the underlying assumption that if you see an absorption feature somewhere in the accumulated catalogue of known chemistry, something will eventually match it. Bézard's team pointed Webb's NIRSpec and MIRI instruments at a spectral window around 5 micrometers, a region of the infrared spectrum that earlier telescopes lacked the sensitivity to study in useful detail, and one that had consequently gone almost unexplored on both Titan and Pluto. What they found, sitting at precisely 511 micrometers, was an absorption band that did not correspond to anything in the catalogue. Not once, on one world, which might reasonably be dismissed as an instrumental quirk or an unlucky coincidence of overlapping known signals. Twice, on Titan, Saturn's giant, orange, atmosphere-shrouded moon, roughly 1 billion kilometers closer to the Sun than Pluto, and independently on Pluto itself, a world with a barely there atmosphere and a surface chemistry that on paper should have almost nothing in common with Titan's dense, methane-soaked environment. Consider, for a moment, how different these two worlds actually are. Titan possesses a nitrogen-methane atmosphere roughly 1.5 times thicker than Earth's own, dense enough to support rivers, lakes and entire seas of liquid methane and ethane, with vast fields of hydrocarbon sand dunes stretching across its equatorial regions. A world so shrouded in orange haze that Titan's own surface remained essentially invisible to human eyes, until radar and infrared instruments finally pierced the smog during the Cassini mission's years-long tour of the Saturn system. Pluto, by contrast, is a world of near vacuum, its atmospheric pressure roughly 100,000th of Earth's, its surface a patchwork of water ice mountains and nitrogen ice glaciers rather than liquid hydrocarbon seas. If you were designing an experiment specifically to test whether a chemical signature was a genuine, physically meaningful molecular feature rather than a coincidence or contamination artifact, you could hardly choose two more different environments than these. And finding the same unexplained signature independently in both is precisely the kind of result that makes a research team sit up and start double-checking their instrument calibrations rather than immediately celebrating. They double-checked. Bézard's team compared the signature against an extensive library of ices likely to exist in these environments. Simple frozen forms of the hydrocarbons and nitriles known to form through photochemistry in Titan's atmosphere, along with the broader family of tholins already well documented across both worlds. None of them matched cleanly. A few compounds came reasonably close without quite fitting, among them a family of hydrocarbons called allenes, molecules containing a distinctive arrangement of carbon-carbon double bonds, and some combination involving benzene, the familiar ring-shaped hydrocarbon possibly mixed with something else entirely. Acetylene ice was floated as another candidate, so was ketene, a reactive, sharp-smelling compound rarely considered in the context of outer solar system surfaces. None of these possibilities, as of the discovery's publication, could be confirmed, and Bézard was refreshingly candid about the state of the investigation, telling one interviewer, in language stripped of academic hedging, that they simply could not yet say what the substance was. There is a detail buried in the data that I find, honestly, more unsettling than the mystery itself, and it deserves careful attention before we move past it. The absorption feature on Pluto was measured as roughly 3 times thicker, meaning more abundant, more concentrated, than the equivalent signature on Titan, suggesting that whatever this substance is, Pluto's surface holds considerably more of it than Titan's does, despite Titan possessing the far richer, far more chemically active atmosphere generally assumed to be the more prolific factory for exotic organic compounds in the outer solar system. And on Titan specifically, the signature wasn't even distributed evenly. It showed up more strongly on the Moon's trailing hemisphere, the side facing away from its direction of orbital travel around Saturn, than on its leading hemisphere, a lopsided pattern that hints at some directional process, perhaps bombardment by charged particles trapped in Saturn's magnetosphere, perhaps something else entirely, shaping where this mystery compound accumulates. Nobody currently knows why. It is, at this stage, simply an observed asymmetry sitting on top of an unidentified molecule, a mystery layered on top of a mystery, and that stacking is precisely the kind of complexity that keeps a genuine scientific puzzle from resolving itself quickly. Here is why I think this discovery deserves more attention than it has so far received outside specialist circles, and why I keep returning to it while writing this, in an era when astronomers routinely announce the detection of dozens of specific molecules in exoplanet atmospheres light years away. Water vapour, carbon dioxide, even the tentative hints of biological signatures on worlds we will never visit in any of our lifetimes. It is a strange and clarifying kind of humility to be reminded that we still cannot fully catalogue the chemistry sitting on the surface of a world we have already flown a spacecraft directly past. Pluto is not some abstraction glimpsed through a gravitational microlensing event or inferred from a transit light curve. New Horizons flew within 12,472 kilometres of its surface in 2015. We have close-up photographs of its mountains, and we still, as of this telling, cannot name a molecule sitting in plain sight on its ice. The researchers are not simply shrugging and moving on, which is itself worth noting, because the standard scientific response to an unidentified signal is rarely to abandon it. It's to attack it from multiple directions simultaneously. Bézard's group is now collaborating with a separate team led by Jonathan Lunine at NASA's Jet Propulsion Laboratory to study how the mystery compound is distributed across Titan's surface, hunting for correlations with known geological features, the dune fields, the lake basins, the specific terrains where the signature intensifies or fades, in the hope that a spatial pattern might narrow down the list of chemical candidates even before a laboratory identification is achieved. Simultaneously, cryogenic chemistry laboratories on Earth are being tasked with attempting to replicate the extreme cold and specific compositional mixtures found on both Titan and Pluto in the hope of physically synthesizing whatever this substance turns out to be and measuring its spectrum directly, rather than continuing to guess from a distance of hundreds of millions to billions of kilometers. And there is a mission already approved and under construction that may eventually settle at least part of this question directly: NASA's Dragonfly, a drone-like, rotor-powered lander scheduled to arrive at Titan's surface in the mid-2030s, capable of flying between dozens of separate landing sites across the Moon's dune fields and lake beds, sampling surface material directly rather than reading it from orbit. There is, however, a frustrating asterisk attached to that hope. Dragonfly, as currently designed, does not carry an infrared spectrometer capable of directly detecting the 511 micrometer feature the way Webb can from 1.5 million kilometers away. It may confirm the mystery compound's presence indirectly, through other instruments capable of analysing surface composition on the ground. But the direct spectroscopic signature that started this entire investigation may remain, for the foreseeable future, something we can only observe from a very great distance. I will admit that this is the point in researching this story where I had to sit back and reconsider what solved actually means in planetary science. We tend to imagine discovery as a door swinging open, mystery on one side, answer on the other, and once the door opens, the room is fully lit. What Bezard's team and Zhang's team before them, and the researchers tracking Charon's red poles before both of them, have actually handed us is something closer to a hallway with more doors at the far end than existed when we started walking, confirming the haze thermostat didn't close the case on Pluto's atmosphere. It opened questions about Titan's and Triton's atmospheres too. Refining the methane transfer model between Pluto and Charon didn't finish the story of Mordor Macula. It revealed how narrow, how seasonally specific, how thermally delicate the mechanism actually is. And now, sitting directly on the ice of both worlds, is a compound that matches nothing we've ever catalogued in any laboratory, on any planet, around any star we've yet examined closely enough to check. But even this unidentified molecule, as strange as it is not the discovery that gives this story its title. And it is not the discovery that unsettled the research community most severely in the past year. That distinction belongs to something else entirely, something found not in a spectrum but in a set of dark, streak-like markings on the surface of Sputnik Planitia, markings that, according to a paper published in August of 2026, appear to have been made by liquid. On a world where liquid, by every established rule of physics governing Pluto's temperature and pressure, should not be able to exist at all. Before we descend into the mechanics of impossible liquid on an impossible world, I want to step back and spend some time with the people who made all of this possible, because I think the science loses something essential if we treat it as though it simply arrived fully formed out of the void. It didn't. It arrived because a small number of deeply stubborn human beings refused to let a distant, unglamorous, repeatedly disrespected little world go unexplored, and their story, decades long, occasionally bitter, ultimately triumphant, sits underneath every discovery this documentary has described so far. Alan Stern first proposed a dedicated mission to Pluto in 1989, while working as a young planetary scientist watching the Voyager 2 spacecraft complete its historic tour of the outer planets with a flyby of Neptune. Voyager had visited Jupiter, Saturn, Uranus and Neptune, every classical planet in the outer solar system except one. Pluto, at the time still universally regarded as the 9th planet, had been left out of the grand tour entirely, a gap in humanity's first reconnaissance of the solar system's outer reaches that Stern found difficult to accept. What followed was not a swift, well-funded mission approval. It was 15 years of proposals rejected, budgets cancelled, alternative mission concepts studied and abandoned, political fights inside NASA's Planetary Science Division, and a persistent institutional skepticism that a small, icy world at the edge of the solar system was worth the enormous cost and multi-year commitment a dedicated mission would require. I find something quietly instructive in just how close this mission came to never happening at all. In 2000, NASA actually cancelled a Pluto mission concept called Pluto Kuiper Express, citing cost overruns, and for a stretch of months it looked as though no American spacecraft would ever visit the 9th planet within the professional lifetime of the scientists who had spent their careers advocating for exactly that. Stern and his colleagues fought the cancellation, rallying scientific societies, lobbying Congress, and eventually succeeding in getting a new, more cost-constrained mission concept approved under NASA's New Frontiers program, the mission that would become New Horizons. It launched on the 19th of January 2006, riding an Atlas V rocket off the pad at Cape Canaveral, accelerating away from Earth faster than any human-made object before it, fast enough to reach the Moon's orbit in roughly 9 hours, a journey that took the Apollo astronauts 3 days. Barely 7 months after that launch, In August 2006, the International Astronomical Union voted in Prague to strip Pluto of full planetary status, meaning that New Horizons, already in flight, already committed to nearly a decade of travel across the solar system, was now officially en route to a dwarf planet rather than the ninth planet it had been designed and funded to explore. Stern has never made peace with that reclassification and has spent years afterward publicly and pointedly arguing that the IAU's 2006 definition of a planet is scientifically incoherent, noting, among other objections, that under a strict reading of the criteria used to demote Pluto, Earth itself would arguably fail the same test. Since Earth's orbit is not entirely clear of debris either, I happen to find his argument more persuasive than dismissive commentators tend to give it credit for, though I recognise that's a matter of ongoing, genuinely unresolved scientific debate rather than settled fact. What moves me most, though, isn't the taxonomy fight, it's the detail that made it into the spacecraft's payload almost as an afterthought. Tucked away among the scientific instruments, a small aluminum canister containing roughly 1 ounce of the cremated remains of Clyde Tombaugh, the same young Kansas farm boy who had discovered Pluto 76 years earlier while hunched over a blink comparator in a cold Arizona dome. Tombaugh died in 1997, 9 years before New Horizons launched, having spent much of his later life hoping that a spacecraft would eventually visit the world he'd found. His widow, Patricia, gave permission for a portion of his ashes to travel aboard the mission, engraved with an inscription that reads, in part, "Interned herein are remains of American Clyde W. Tombaugh, discoverer of Pluto and the solar system's third zone." I have read that inscription more times than I probably need to admit, and it still catches something in my chest each time. The idea that a person who spent a winter of his youth in patient, unglamorous obsession, squinting at photographic plates by lamplight, would eventually be carried, however symbolically, past the very world he found, at a speed and distance that nothing in his lifetime could have prepared him to imagine. New Horizons crossed 4.67 billion kilometres of space over 9.5 years, and on the 14th of July 2015, it executed its closest approach to Pluto, a single, irrevocable pass, since the spacecraft carried no fuel budget for orbital insertion and would fly past at roughly 13.78 kilometers per second, never to return. There was no second chance built into the mission design. If a camera malfunctioned, if a data storage system failed, if the spacecraft's trajectory calculations were off by even a small margin, the flyby would be over before anyone on Earth even knew something had gone wrong, and there would be no way to try again. I want to dwell on the tension of that morning for a moment, because it is easy, in hindsight, to treat the flyby as a foregone success. We have the photographs, after all, so clearly it worked. But on the day itself, the mission team spent the hours around closest approach in something close to enforced silence, because New Horizons, during the flyby window itself, was oriented to point its instruments at Pluto rather than its antenna at Earth, meaning the spacecraft could not communicate with mission control during the exact moment its entire decade-long purpose was being fulfilled. Alan Stern has described that stretch of radio silence, roughly 22 hours between the spacecraft's last confirmed status update before closest approach and its first post-flyby signal, as the longest and most anxious hours of his professional life. There was nothing anyone on Earth could do in that window except wait, recalculate, second guess, and hope that a piece of hardware travelling faster than a rifle bullet, 9.5 years and 4.67 billion kilometres from home, had executed a sequence of commands programmed months in advance, with no possibility of correction, no margin for human intervention if something had drifted out of tolerance. When the signal finally arrived confirming the spacecraft had survived the flyby and successfully collected its data, the control room at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, erupted, and Stern, by his own account, found himself unexpectedly emotional, the culmination of 26 years of advocacy, setbacks, and stubborn persistence compressed into a single confirmed radio signal. crossing 4.5 hours of empty space. I think what this human story offers, beyond the simple pleasure of a well-earned triumph, is a kind of counterweight to how coldly we sometimes talk about scientific discovery, as though data simply accumulates, papers simply get published, and understanding simply advances on its own momentum. It doesn't. Every discovery this documentary has described so far, from Zhang's haze thermostat to Bazar's unidentified molecule to the liquid nitrogen findings we're about to explore, exists because specific, named human beings refuse to let a question go unanswered, sometimes across decades, sometimes against direct institutional opposition, sometimes at real personal and professional cost. Xi Zhang held on to an idea his peers openly doubted for 8 years before a telescope existed capable of testing it. Alan Stern spent 15 years fighting cancellations and budget fights before his mission ever left the launch pad, and then endured 22 hours of silence, not knowing whether that decades-long effort had succeeded or been erased in an instant by a single malfunction. This is, to my mind, one of the most quietly heroic aspects of modern planetary science, not the discoveries themselves, but the sheer unglamorous persistence required to make them possible in the first place. And Stern's involvement with Pluto did not end when New Horizons completed its flyby in 2015. The spacecraft, still functioning, still transmitting, continued outward into the Kuiper Belt, executing a second, smaller flyby of a distant snowman-shaped object called Arakoth on New Year's Day, 2019, the most distant object ever explored up close by a spacecraft from Earth at the time. And Stern himself, rather than retiring from Pluto research once the primary mission objectives were achieved, remained deeply engaged with the world he had spent a professional lifetime advocating for, returning in 2026 as the lead author on the very paper that describes what may be the single strangest discovery in this entire documentary, fresh evidence, drawn from a fresh reanalysis of the New Horizons imagery he had waited so long to obtain, that liquid nitrogen may be actively rising to the surface of Sputnik Planitia even now, more than a decade after the flyby, on a world where liquid of any kind should be physically forbidden. Pluto never stopped surprising us, Stern said when the study was announced, and I don't think that sentence should be read as a scientist's polite understatement. I think it should be read, almost literally, as the honest reaction of a person who has now spent close to 4 decades of his working life on this single small world, who fought institutional indifference to get a mission built, who sat through the longest silence of his career, waiting to learn if that mission had survived its own defining moment, and who is still, this many years later, finding that the world he helped humanity finally see up close refuses to stop behaving in ways nobody predicted. That refusal, Pluto's stubborn, ongoing capacity to violate expectations, is where we're headed next, and it is, without exaggeration, the strangest single finding in this entire investigation. Liquid nitrogen, under the pressure and temperature conditions that exist at Pluto's surface today, is not supposed to be possible. This is not a subtle point of scientific nuance open to interpretation. It is basic phase physics, the same kind of chart you'd find in an introductory chemistry textbook, describing the boundaries between solid, liquid, and gas for any given substance under specific combinations of pressure and temperature. At the atmospheric pressure measured on Pluto's surface, roughly 1 Pascal, and at the surface temperatures New Horizons and subsequent modelling have measured, nitrogen simply cannot exist as a stable liquid out in the open. It exists as ice, or it sublimates directly into vapour, skipping the liquid phase entirely the way dry ice does on Earth. That is the physics every model of Pluto's surface has operated under, since New Horizons first characterised the atmosphere in 2015. And in August of 2026, a team led by Alan Stern published a paper describing surface features on Sputnik Planitia that look, in every meaningful visual and structural respect, exactly like they were made by liquid flowing across ice. The features themselves sit along the northern edge of Sputnik Planitia, the vast nitrogen ice glacier, larger than the states of Texas and Oklahoma combined, that dominates the western lobe of Pluto's famous heart-shaped region. New Horizons imagery from 2015 had already revealed that this glacier is broken into a mosaic of polygonal convection cells, each one 30 to 40 kilometers across, separated by narrow troughs where warmer nitrogen ice rises from below, spreads outward, cools and sinks again, a process directly analogous to the convection you'd see in a lava lamp, except operating in solid but slowly flowing nitrogen ice rather than heated wax. What Stern's newly reanalyzed data showed, along the northernmost margins of this convecting glacier, were dark, narrow, linear features running alongside more diffuse dark patches, and when the research team compared these markings against high-resolution Landsat 9 satellite imagery of terrestrial ice sheets, specifically regions of the Greenland ice sheet, where scientists have independently confirmed the presence of liquid water darkening the surface through meltwater channels and slush zones. The visual and structural resemblance was, in the team's own assessment, striking enough to warrant serious investigation rather than dismissal. Kelsey Singer, a principal scientist at the Southwest Research Institute and co-author on the study, placed the discovery in a broader geological context that matters enormously for understanding why this finding carries the weight it does. The surface of Sputnik Planitia, based on modelling of how quickly the convection cells overturn and erase older terrain, is almost certainly less than 1 million years old, geologically speaking, an eye blink, especially against the backdrop of a 5 billion-year-old solar system. Whatever process created these dark, liquid-looking features had to have operated within that narrow, recent window, and quite possibly is still operating today, or was operating recently enough that the marks have not yet been erased by the glacier's own slow overturning. Pluto has many unique terrains seen nowhere else in the solar system, Singer noted, and this area of Sputnik Planitia is one of them, a description that, once you understand what the team believes is happening beneath the surface, feels almost understated. So how, precisely, does liquid nitrogen exist on a world where the surface conditions explicitly forbid it? The answer the research team proposes lies not on the surface, but hidden beneath kilometers of accumulated nitrogen ice in a physical regime governed by pressure rather than atmosphere. Computer models developed by Orkan Umahan, a senior research scientist at the SETI Institute, suggest that at the base of Sputnik Planitia's ice sheet, which in places may run several kilometers deep, the immense weight of overlying ice generates enough pressure, combined with whatever modest geothermal heat Pluto's interior still retains, to push conditions at that specific depth across the melting boundary, allowing solid nitrogen ice at the base of the glacier to transition into liquid nitrogen, sealed away from the vacuum-adjacent atmosphere above by kilometers of insulating ice. It is a phase transition happening, not because the temperature has changed dramatically, but because the pressure at depth has crossed a threshold the surface conditions never approach. Once that liquid nitrogen exists at depth, Umahan's models describe a transport mechanism that should sound eerily familiar to anyone who has read about terrestrial volcanism or geyser activity. The liquid, buoyant relative to the solid ice surrounding it, gets driven upward through small conduits, natural channels within the ice sheet, functioning much like lava tubes or geyser plumbing here on Earth, pushed by pressure differentials and buoyancy forces until it reaches the surface. And crucially, the models suggest that once this liquid nitrogen breaks through to the surface, it can persist in a liquid state for long enough, even in Pluto's brutally hostile surface conditions, to actually flow downhill across slopes on the glacier's surface before it finally freezes or sublimates away entirely, flowing just long enough to wet the surrounding ice, darkening it in exactly the pattern the New Horizons images captured, before the liquid nitrogen's brief, doomed existence in the open air comes to an end. I want to pause here and be honest about how strange this proposal actually is, because it is easy to read a summary like the one I've just given and let the science documentary cadence smooth over just how counterintuitive the underlying claim really is. We are describing a mechanism where a substance that comprises the bulk of the air you and I breathe, on Earth existing as a permanent gas, under virtually every condition a human being ever encounters, becomes a solid so cold that ice made from it can flow like a terrestrial glacier, then melts at its base under sheer pressure into a liquid, then gets physically pumped upward through the ice sheet by buoyancy in a process resembling a planet's plumbing system, then briefly emerges onto the surface of a world 4 billion kilometers from the Sun, flows downhill for some short but geologically meaningful distance, wetting and darkening the ice around it, and then vanishes, refreezing or subliming away, leaving behind nothing but a dark stain and a research team a decade after their spacecraft flew past, staring at old photographs and only now recognizing what they were actually looking at. Orkan Umahan's own reaction to the finding, as recorded in the study's supporting materials, strikes me as an unusually candid summary of where the science currently stands. He describes the discovery as a great motivation and reason to further examine solid-state nitrogen physics at very low temperatures, and specifically points out that the physics of nitrogen ice, melting and flowing under stress and strain, have never been studied in real detail in the laboratory. Sit with that admission for a moment. We are talking about one of the simplest, most abundant molecules in the universe. Nitrogen makes up roughly 78% of the air around you right now, and yet its behaviour under the specific, extreme pressure and cold conditions that exist at the base of a kilometres-deep glacier on a dwarf planet has essentially never been directly tested in a laboratory setting on Earth. The physics underpinning this entire discovery is, in a very real sense, still theoretical, built on models and analogies to terrestrial ice sheets rather than direct laboratory confirmation, because nobody has ever needed to build an experiment cold enough and pressurized enough to test it before now. This is, I think, one of the places where the stakes of this whole investigation genuinely escalate beyond an interesting quirk of one distant world into something with much broader implications, and here is why. If liquid nitrogen can exist beneath Pluto's surface, sealed away from the hostile vacuum above by an insulating cap of ice, kept liquid purely through pressure and whatever modest internal heat the dwarf planet retains, then the same basic physical principle should, in theory, apply to other icy bodies across the outer solar system that share similar characteristics: sufficient ice thickness, sufficient interior heat, sufficient overlying pressure. The research team explicitly pointed toward Neptune's large moon Triton as a natural next candidate, since Triton hosts geysers, first documented by NASA's Voyager 2 spacecraft during its 1989 flyby, that eject dark plumes of material dozens of kilometers into space. Plumes long suspected to involve some combination of nitrogen ice sublimation and subsurface pressure release, but never fully explained by any single confirmed mechanism. If the basal melting and buoyant transport model developed for Pluto's Sputnik Planitia turns out to apply more broadly, it would offer, for the first time, a physically grounded explanation for one of the outer solar system's other long-standing mysteries. But the implications reach further than just explaining Triton's geysers, and this is where I think the discovery earns its place at the centre of this entire documentary. For decades, the search for potentially habitable environments beyond Earth has focused overwhelmingly on the presence of liquid water, the assumption, built into missions targeting Europa, Enceladus and Mars, being that water is the essential solvent life as we understand it requires. That assumption isn't wrong exactly, but Pluto's newly discovered liquid nitrogen forces a broader, more uncomfortable question into the conversation. If a solid body this small, this cold, this far from any conventional heat source can generate and sustain liquid, any liquid, under the right combination of pressure and insulation, at some depth beneath its surface, then the range of worlds across the solar system, and by extension across other planetary systems that might harbour some form of subsurface liquid environment, could be substantially larger than current habitability models account for, not necessarily habitable in the biological sense. Liquid nitrogen at -200 degrees Celsius is not a solvent anyone seriously proposes could support the biochemistry we understand as life. But the underlying mechanism, pressure-driven melting at depth, buoyant transport to the surface through natural conduits, brief liquid expression before refreezing, is a template. And templates, once discovered on one world, have an unfortunate habit of turning up again on others. We assumed were far too simple, far too cold, far too dead to bother looking closely at. I find myself genuinely unsettled by this, in the specific way that good science is supposed to unsettle you. And I don't think that's an overstatement given what's at stake here. We built our entire framework for where to search for potentially interesting chemistry and biology in the solar system around the presence of liquid water and around bodies large enough and warm enough to sustain internal oceans through tidal heating, the mechanism believed to keep Europa's and Enceladus's subsurface oceans liquid. Pluto is not large. Pluto is not tidally heated by a nearby giant planet the way Europa and Enceladus are. Pluto is, by every conventional metric astronomers have used for decades to sort worlds into interesting and boring categories, about as unpromising a candidate for active subsurface liquid processes as the solar system offers, and it appears to have them anyway. If Pluto can defy the categories we built to predict which worlds deserve close attention, how many other small, cold, supposedly geologically dead bodies scattered across the Kuiper belt, Eris, Makemake, Haumea, and the thousands of smaller objects we have barely begun to characterize, might be quietly doing something similar, undetected, simply because nobody thought to look closely enough? That question does not have an answer yet. It may not have one for decades, given how few spacecraft missions are currently planned or funded to visit the outer Kuiper belt in any detail, beyond what New Horizons and Webb have already provided. But the question itself represents a genuine escalation in stakes from where this documentary began. We started with a demoted dwarf planet whose atmosphere turned out to have an unexpected thermostat. We are now looking at a small, distant world that may be actively generating and expelling liquid through a subsurface plumbing system nobody predicted, using physics nobody has tested in a laboratory, with implications that stretch outward toward every other icy body in the outer solar system we thought we understood well enough to ignore. And underneath all of it sits a molecule on the surface of both Pluto and Titan that still, as of this telling, has no name. Let me be honest about something that responsible science communication requires, and that I think matters enormously given everything we've covered so far. Not every claim in this story carries the same weight of certainty, and treating them all as equally settled would do a disservice to the actual, careful, occasionally uncomfortable process by which these findings are being tested, challenged, and refined by the scientific community in real time. So let's slow down and examine, with real rigour, exactly how solid each of these three central discoveries actually is, what the strongest counterarguments and alternative explanations look like, and where genuine, unresolved scientific disagreement still exists. Start with the most mature of the three findings, the haze-driven thermostat model for Pluto's atmosphere. This is, by a considerable margin, the most thoroughly vetted claim in this documentary, and for good reason. It originated as a specific falsifiable prediction made by Shi Zhang in 2017, sat untested for 8 years for lack of a sufficiently sensitive instrument, and was then confirmed through a carefully constructed observational campaign using Webb's MIRI instrument, culminating in peer-reviewed publication in Nature Astronomy, one of the more rigorously reviewed journals in the field, in June of 2025. The path from hypothesis to confirmation here followed something close to the ideal scientific process. A specific mechanism proposed, a specific observable consequence predicted, years of patient waiting for the right tool, and then a direct test against real data that either would or would not match the prediction. It matched. That doesn't mean every detail of the haze model is now beyond dispute. Researchers are still working out exactly how the haze particle sizes, compositions, and vertical distribution vary across Pluto's seasons, and Zhang himself has pointed toward Titan and Triton as places where the same basic framework needs independent testing before anyone declares the underlying physics universally applicable to hazy nitrogen atmospheres. But the core claim that Pluto's haze, not its bulk gas, dominates the atmosphere's thermal energy budget now sits on genuinely solid observational footing, about as close to settled as anything in this documentary gets. The Karen methane transfer and light curve findings occupy a slightly more complicated position. The broad mechanism, Pluto's atmosphere leaking methane, some fraction of it reaching Charon's polar cold traps, undergoing radiation-driven chemical transformation into reddish tholins, was already reasonably well supported by New Horizons data going back to 2015, and Webb's contribution here was less about overturning that basic picture than about refining it with genuinely new, precise numbers. Separate thermal light curves for Pluto and Charon, better constraints on thermal inertia, and confirmation of Linfeng 1's 2023 predicted light curve amplitude. This is real, meaningful scientific progress, but it's worth being precise about what it does and doesn't establish. It confirms that the methane transfer framework produces thermal signatures consistent with what Webb actually measured. It does not yet fully resolve exactly how much methane is transferred at different points in Pluto's 248-year orbital cycle, nor does it fully account for whether other, currently unidentified compounds, including, potentially, whatever is responsible for that mysterious 5.11 micrometer absorption feature, might be contributing to Charon's polar coloration alongside the methane-derived tholins already well documented. In other words, the mechanism is confirmed in broad strokes and refined in specific measurable ways, but the full chemical inventory of Mordor Macula's red staining may not yet be completely accounted for. Now to the mystery molecule itself, which carries, by the researchers' own explicit statements, the least certainty of anything discussed in this documentary, and I think it's important to sit with that honestly, rather than smoothing it over for dramatic effect. Bezar's team published their findings as a preprint on Arxiv in June of 2026, before securing acceptance into Astronomy and Astrophysics the following month. A legitimate standard path to publication, but one that means the finding, while now peer-reviewed, is genuinely fresh, has not yet been independently replicated by a separate research group using separate data, and remains, in the researchers' own words, unidentified. This is not a weakness in the science. Unresolved, honestly labelled uncertainty is exactly what responsible research is supposed to look like at this early stage of an investigation. But it does mean that when this documentary describes an unidentified molecule, it means precisely that. Not a molecule whose identity is merely awaiting confirmation of an already strong leading candidate, but a genuine gap in the periodic table of possibilities available to explain a real, repeatedly measured, statistically significant absorption feature. The leading candidates, benzene mixtures, acetylene ice, ketene, the alene family of hydrocarbons, remain candidates precisely because none of them cleanly reproduces the observed spectral characteristics. And Bezar has been direct in interviews about the genuine, current absence of a satisfying answer. There is also a subtler methodological question worth raising here, one that experienced spectroscopists would recognise immediately, and that deserves airing rather than glossing over. Could this unidentified feature be an artifact of some combination of known molecules interacting in an unusual physical environment, rather than evidence of a genuinely novel, previously unseen compound? Bezar's own comments hint at exactly this possibility, noting that the team considered scenarios involving a molecule within a mixture of ices whose spectral properties are profoundly altered by its physical environment. Meaning the mystery might not necessarily require inventing an entirely new molecule from scratch, but could instead involve an already known substance behaving in a spectroscopically unfamiliar way because of how it's mixed, frozen, or irradiated on Titan's and Pluto's specific surfaces. That distinction matters enormously for how we should understand the scale of what's been found. A genuinely novel compound would represent chemistry previously unknown to exist anywhere in the observable universe. A known compound behaving unexpectedly under extreme cold and radiation would represent something almost as scientifically valuable. A gap in our understanding of how familiar chemistry behaves at the far edge of temperature and pressure extremes, but a categorically different kind of discovery. As of this telling, the research genuinely cannot distinguish between these two possibilities, and I think intellectual honesty requires saying so plainly rather than resolving the ambiguity for the sake of a cleaner narrative. Finally, and most consequentially for the central claim woven through this entire documentary, the liquid nitrogen findings on Sputnik Planitia. This is, without question, the newest, least independently verified, and most audacious of the three major discoveries covered here, and it deserves the most careful scrutiny precisely because it is also the most dramatic. Consider first what the evidence actually consists of: dark, linear, and diffuse surface features in New Horizons imagery from 2015 and 2016, reanalyzed more than a decade later, and compared visually and structurally to terrestrial ice sheet meltwater features documented via Landsat 9 satellite imagery of Greenland. This is, in the strictest sense, an inference built on morphological analogy. The Sputnik Planitia features look like features on Earth that we independently know are produced by liquid water, combined with a physically plausible, computationally modelled mechanism proposed by Orkun Numurhan, explaining how liquid nitrogen specifically could form and reach the surface under Pluto's conditions. It is not, and this distinction matters enormously, a direct spectroscopic detection of liquid nitrogen itself. Nobody has measured a spectrum showing liquid phase nitrogen sitting on Pluto's surface in the way Bezard's team measured an absorption feature at 5.11 micrometers. The claim rests on visual pattern matching plus a supporting physical model, published in the peer-reviewed Planetary Science Journal, which lends it real scientific weight, but which is a fundamentally different, and in some ways more fragile, form of evidence than a direct spectroscopic detection. I want to be careful here not to suggest the finding is weak, or that the researchers behind it are overreaching, because that would misrepresent both the quality of the work and the caution with which it was actually presented. Stern and his co-authors explicitly frame the study as providing evidence for possible basal nitrogen flow, the word possible doing real deliberate work in that title, a linguistic hedge that responsible scientists include precisely when they want readers to understand that a compelling case has been built, but that the case remains, by the nature of the evidence available, short of definitive proof. Kelsey Singer's framing of Sputnik Planitia's surface as young, likely under 1 million years old, strengthens the plausibility that whatever process created these features could be recent or ongoing, but plausible and recent is not the same standard of evidence as directly confirmed. The honest summary, and I think this is worth stating plainly rather than letting the drama of the discovery obscure it. This is a strong, well-reasoned, peer-reviewed hypothesis built on genuine morphological and physical modelling evidence, representing the current leading explanation for a real and puzzling set of surface features, but it is not yet a confirmed detection of liquid nitrogen in the way that, say, the Cassini mission directly detected liquid hydrocarbon lakes on Titan's surface through radar reflectivity measurements that left comparatively little room for alternative interpretation. What would settle the question more definitively? Ideally, either a future spacecraft mission capable of directly imaging Sputnik Planitia at far higher resolution than New Horizons' single 2015 flyby achieved, watching for active surface change over a period of months or years, rather than inferring past activity from a single historical snapshot or a spectroscopic instrument sensitive enough to detect the specific signature of liquid phase nitrogen directly, rather than inferring its presence from surface darkening patterns alone. Neither capability currently exists in any funded operating mission. New Horizons has already flown past and continues outward into deeper space, its Pluto reconnaissance permanently complete. Webb, while extraordinarily powerful, was not designed with the specific spatial resolution needed to resolve fine surface detail on a world as small and distant as Pluto. Its strength lies in spectroscopy and thermal light curves, not high-resolution surface imaging comparable to what a dedicated orbiter could provide. Which means, as things currently stand, the liquid nitrogen hypothesis will likely remain in this evidentiary position, strongly supported, physically plausible, peer-reviewed and genuinely unconfirmed, for the foreseeable future, absent a new mission specifically designed to return to Pluto and watch it change over time. And this, I think, is where the deepest, most important complication in this entire documentary finally surfaces, one that connects all three discoveries back together into a single, coherent, and genuinely humbling scientific situation. Every major finding described here, the Hayes thermostat, the Karen methane transfer refinements, the mystery molecule, the liquid nitrogen hypothesis, shares a common structural feature. Each one was made possible not by a single triumphant, decisive observation, but by returning to old data or gathering new but still indirect data, and finding that our previous, confident models of a small, supposedly simple world were incomplete in ways nobody had anticipated. Zhang's Hayes model sat dormant for 8 years, unconfirmed, because the tool needed to test it didn't exist yet. The Karen light curves required Webb's specific spectral and photometric sensitivity to separate two overlapping thermal signals that had been blurred together in every previous observation. Bazar's mystery molecule sat hidden in a spectral window nobody had previously had the sensitivity to examine closely. And Stern's liquid nitrogen hypothesis required someone to go back, more than a decade after the original flyby, and look at old New Horizons images with new eyes, informed by satellite comparisons to Greenland that nobody had thought to make in 2015 or 2016. I find something almost philosophically unsettling in that pattern, and it's worth dwelling on directly rather than rushing past it. We tend to imagine scientific progress as a forward march, new missions, new telescopes, new data, new discoveries, each one building cleanly on the last. What this particular sequence of Pluto research actually demonstrates is something closer to the opposite, that our understanding of even a world we have already visited up close, already photographed in exquisite detail, already characterized across multiple published scientific papers, remains genuinely, substantially incomplete. Not because we lack data, but because we lack the specific instruments, the specific comparative frameworks, or simply the specific willingness to look again with fresh eyes until years after the fact. Pluto was not hiding these phenomena from us in any meaningful sense. We simply weren't yet equipped, technologically or conceptually, to recognize what we were looking at. And if that's true for a world as thoroughly studied as Pluto, flown past by a dedicated spacecraft, repeatedly observed by the most advanced space telescope humanity has ever built, it raises an uncomfortable, genuinely open question about how much we might still be missing across every other body in the solar system we've only glimpsed from a distance, or haven't visited at all. That question, how much are we still missing, even in the places we think we've already explored, is the thread that carries this documentary into its final movement. Because it turns out the answer isn't going to arrive quickly, and the tools currently being built to chase it are further out on the horizon than most people realise. The honest, unglamorous truth about where Pluto research stands as of this telling is that there is currently no funded, approved mission specifically designed to return to the dwarf planet and resolve any of the three major open questions this documentary has traced, not the mystery molecule's identity, not the full extent of the liquid nitrogen hypothesis, not the finer mechanics of the Hayes thermostat across a full Plutonian season. New Horizons completed its primary reconnaissance in 2015, executed a bonus flyby of the Kuiper Belt object Arakoth in January 2019, and continues travelling outward even now, its instruments periodically returning data about the heliosphere and interplanetary medium, but its Pluto science is, for all practical purposes, permanently closed. There is no return trip scheduled. if you want a second, more detailed look at Sputnik Planitia, watching for active change rather than inferring it from a single-decade-old snapshot, that mission does not currently exist on any space agency's funded timeline. This is not for lack of scientific appetite. Since the New Horizons flyby, planetary scientists have repeatedly proposed follow-up missions, ranging from dedicated Pluto orbiters capable of mapping the entire surface at high resolution over an extended period, to more ambitious concepts involving a lander capable of directly sampling Sputnik Planitia's surface chemistry, potentially settling the liquid nitrogen question with direct measurement rather than morphological inference from old photographs. None of these concepts have yet secured the kind of sustained funding commitment that would move them from proposal to hardware. Part of the challenge is straightforwardly practical. Any mission designed to orbit Pluto, rather than simply fly past it as New Horizons did, requires an enormous amount of propellant to decelerate upon arrival after a multi-year cruise, a technical and budgetary hurdle considerably steeper than the one New Horizons faced, since a flyby mission needs only enough fuel for course corrections along the way, not a full braking manoeuvre at journey's end. Solving that propulsion problem, whether through more efficient engines, nuclear electric propulsion, or some combination of gravity assist trajectories through the outer solar system, remains an active area of mission design study rather than a solved engineering question with a funded spacecraft attached to it. In the nearer term, the most concrete piece of new hardware likely to advance our understanding of these questions isn't headed to Pluto at all. It's Dragonfly, NASA's rotorcraft mission to Titan, currently scheduled to arrive at Saturn's largest moon in the mid-2030s after launch. Dragonfly represents a genuinely novel approach to planetary exploration, rather than landing once and staying fixed in a single location the way most previous landers have. It will use its rotors to fly between dozens of separate sites across Titan's dune fields and impact crater terrain, sampling surface material directly at each stop and analysing its chemical composition on the ground. Given that Titan shares the mystery 5.11 micrometer absorption feature with Pluto, Dragonfly's direct surface sampling could, in principle, offer real insight into whatever compound or family of compounds is responsible. But as noted earlier, the mission's current instrument suite does not include an infrared spectrometer specifically tuned to directly redetect the 5.11 micrometer signature the way Webb does from orbit, meaning any contribution Dragonfly makes to identifying the mystery molecule will likely be indirect, inferred from broader compositional analysis rather than a clean, direct match to the specific spectral feature that started this entire thread of investigation. Webb itself, meanwhile, remains the single most capable instrument currently available for continued Pluto and Titan observation, and mission planners have every incentive to keep returning to both worlds across the telescope's operational lifetime, which mission engineers currently estimate could extend 20 years or more, given the spacecraft's fuel-efficient orbit and the surprisingly conservative rate at which its onboard propellant has been consumed since launch. Repeated observations across Pluto's seasons remember an entire Plutonian year spans 248 Earth years, meaning even decades of continuous Webb observation will only ever capture a relatively narrow sliver of the dwarf planet's full seasonal cycle. Could refine the haze thermostat model further, potentially catching the atmosphere in different seasonal configurations as ice migrates between hemispheres over time. Similarly, continued spectroscopic monitoring of the 5.11 micrometer feature on both worlds, especially if paired with the spatial mapping work Bezar's team is already pursuing in collaboration with Jonathan Lunin's group at JPL, could eventually correlate the mystery compound's abundance with specific surface terrains, narrowing the list of plausible chemical candidates even without a direct laboratory identification. There is also a slower, less visible but arguably just as important track of progress happening entirely on Earth, in laboratories rather than in space. the cryogenic chemistry work Orkanu Mohan explicitly called for when describing the liquid nitrogen findings. Building experimental setups capable of replicating the specific pressure and temperature conditions found at the base of a multi-kilometre deep nitrogen ice sheet is a genuinely difficult engineering challenge in its own right, requiring specialised high-pressure cryostats and measurement techniques that, by Umohan's own account, have simply never been developed with this specific application in mind, because nobody has previously needed to study solid nitrogen's mechanical behaviour under these exact extreme conditions. If such experiments are successfully built and run over the coming years, they could directly test whether nitrogen ice under Sputnik, Planetia's estimated basal pressure and temperature, genuinely does melt the way Umohan's computer models predict, converting the current hypothesis from a computationally modelled possibility into an experimentally validated physical mechanism, a meaningfully different and stronger form of scientific confirmation than currently exists. I think it's worth pausing on just how unusual it is, in an era of exoplanet spectroscopy and gravitational wave astronomy, that some of the most consequential open questions in planetary science require, at their core, patient laboratory chemistry conducted at extremely low temperatures here on Earth, rather than more spacecraft, more telescopes, or more distant observation. It is a reminder that the frontier of discovery isn't always further away. Sometimes it's a matter of building the right experimental apparatus in a basement laboratory, replicating conditions that exist naturally only in the outer solar system, and being patient enough to run the numbers correctly. There is something almost humbling in that, a corrective to the assumption that bigger telescopes and farther-flung spacecraft are always the answer. Beyond Pluto and Titan specifically, the broader implications of this research are already beginning to ripple outward into how planetary scientists think about categorizing worlds across the outer solar system, and, more speculatively, in other planetary systems entirely. If the basal melting and buoyant transport mechanism proposed for Sputnik Planitia holds up under further scrutiny, researchers studying Neptune's moon Triton, whose Voyager 2 documented geysers have puzzled scientists since 1989, now have a concrete, physically grounded hypothesis to test against their own data, one that didn't exist in any rigorous form before Stern's 2026 paper. And the Hayes thermostat model Zhang first proposed in 2017 and Webb confirmed in 2025 is already prompting researchers to revisit assumptions about atmospheric energy balance on every other nitrogen and hydrocarbon haze world in the solar system, including Titan itself, where the much thicker atmosphere may behave according to broadly similar principles operating at a dramatically different scale. There is also a more speculative but genuinely serious line of inquiry opening up around exoplanet science, one that Xi Zhang gestured toward when he connected Pluto's chemistry to the conditions of early Earth, roughly 4 billion years ago, before oxygen accumulated in our own planet's atmosphere, and when nitrogen hydrocarbon photochemistry, similar in broad outline to what's happening on Pluto and Titan today, likely dominated Earth's early atmospheric chemistry during the period when life was first establishing itself. Astronomers searching for potentially habitable exoplanets around other stars have increasingly begun considering nitrogen and hydrocarbon-dominated atmospheres, rather than exclusively oxygen-rich ones, as plausible signatures of early biological activity on distant worlds. And the physics being worked out on Pluto's haze, however far removed from any question of life on Pluto itself, is directly informing the atmospheric models astronomers will eventually apply to interpreting Webb's spectra of exoplanets light years away, worlds we will study only through the faint, filtered light passing through their atmospheres during a transit, never through a spacecraft flyby, and certainly never through a landed instrument sampling their surface directly. I keep returning, as I write this, to the strange asymmetry embedded in that last point. The physics we are learning by studying a small, cold, disrespected world we've actually visited with a spacecraft is going to shape how we interpret worlds we will only ever see as a smudge of light thousands of trillions of kilometers away, filtered through instruments straining at the very edge of their sensitivity. Pluto, in that sense, isn't just a destination in its own right. It's becoming something closer to a calibration standard, a nearby, physically accessible test case for chemistry and atmospheric physics that will eventually need to be applied, with far less direct evidence available, to worlds we can never hope to visit within any foreseeable time frame. That is, I think, a genuinely underappreciated role for a world that spent most of the 20th century treated as a minor curiosity at the edge of a solar system diagram, and most of the early 21st century fighting, unsuccessfully, to keep its status as a planet. None of this closes the loop on any of the three central mysteries this documentary has traced. The mystery molecule remains unidentified. The liquid nitrogen hypothesis remains a strongly supported but unconfirmed inference. The full seasonal behaviour of the haze thermostat remains only partially characterised, glimpsed across a handful of years of Webb observation against a planetary season that spans nearly 2.5 centuries. What has changed decisively is the confidence with which anyone can claim Pluto is simple, settled, or fully understood. It isn't, and every indication from the current pace of research suggests that whatever comes next, a laboratory experiment successfully replicating basal nitrogen melting, a spatial correlation narrowing down the mystery molecule's chemical family, a future mission concept finally securing the funding it needs to return to Sputnik Planitia with fresh instruments, will very likely surprise us again in ways nobody currently working on this problem has yet anticipated. There is a particular kind of silence that exists at Pluto's distance from the Sun, and I don't mean this only in the acoustic sense, though that's true too. There is no atmosphere thick enough there to carry sound the way it carries here, no medium dense enough to transmit the small, constant noise that fills every environment human beings have ever evolved to inhabit. I mean something closer to an informational silence, a gap between what light can tell us and what we actually need to know, a gap that widens with every additional kilometre of distance and narrows only through decades of patient, unglamorous, frequently doubted work. Sunlight reaching Pluto's surface arrives some 1,600 times fainter than it does here, faint enough that the difference between day and a bright, starlit night becomes almost a matter of degree rather than kind. And yet, across that faint light, across 4.5 hours of radio delay, across a gap that a signal travelling at the speed of light itself takes longer to cross than most working days, human beings have managed to detect a thermostat running on smog, a moon being chemically stained by its neighbour's exhaled breath, a molecule that matches nothing we've ever catalogued, and, perhaps most remarkable of all, liquid, flowing, however briefly, across a world colder than almost anywhere ice has ever existed. I think there is something worth sitting with in the fact that all of this was discovered not by finding something new to look at, but largely by looking again, more carefully, at something we already thought we understood. Xi Zhang's haze model waited 8 years for the right instrument to test an idea nobody else believed. Bézard's mystery molecule hid in a spectral window nobody had previously examined closely enough. And Alan Stern's liquid nitrogen hypothesis emerged not from a new flyby, not from any fresh spacecraft data, but from returning, more than a decade later, to photographs already sitting in an archive and finally recognising in them a pattern that Greenland's own melting ice sheets had, in effect, taught scientists to see. There's a lesson buried in that pattern that extends well past planetary science, I think. That the limits of what we understand are so often not a matter of missing data, but of missing the specific comparison, the specific question, the specific willingness to look again at something we'd already filed away as settled. It would be easy, and I think it would be a mistake, to treat Pluto's persistent strangeness as merely a curiosity confined to one small, distant world most people will never think about outside of the occasional headline. What this investigation actually reveals, if you sit with the full arc of it, is something closer to a caution about confidence itself. A reminder that settled science, even when it's built on a successful historic spacecraft mission, even when it's been repeated in documentaries and textbooks for a decade, can still be sitting on top of mechanisms nobody has yet thought to test, waiting for a telescope, a computer model, or simply a researcher stubborn enough to look one more time. Every world we think we've finished studying is, in some sense, a claim we haven't fully verified yet. Pluto happened to be the one where the gap between photographed and understood became impossible to ignore. It will almost certainly not be the last. There is something in this story, too, about the strange, quiet dignity of persistence, embodied across 3 human lifetimes now stretched across this single small world at the edge of the solar system. Clyde Tombaugh, spending a winter of patient obsession, squinting at photographic plates for a discovery he could never have known, would carry his own remains past the very object he found. Alan Stern, spending 15 years fighting cancellations and institutional doubt before the mission he'd proposed even left the ground, then decades more returning, again and again, to the world he helped humanity finally see. Xi Jiang, holding on to an idea his peers considered implausible for the better part of a decade, waiting for a telescope that didn't yet exist to prove him right. None of these people knew, at the moment of their most difficult, most uncertain choices, whether the questions they were chasing would ever resolve into an answer within their working lifetimes. Most scientific careers, most human lives generally, don't come with that guarantee. They persisted anyway, because the question itself seemed worth the persistence, regardless of when or whether an answer would eventually arrive. That, I think, is the closest thing to a lesson this story has to offer, and it isn't really a lesson about Pluto at all. It's a lesson about what it means to hold a genuine, unresolved question for longer than feels comfortable, to keep funding it, defending it, testing it, revisiting it, even when the field around you has largely moved on to newer, shinier targets, the exoplanets, the early galaxies, the black holes colliding across billions of light years, because something in you refuses to accept that a small, cold, thoroughly demoted world at the edge of the solar system has told us everything it has to tell. Pluto never asked to be interesting. It simply sat there, 4.5 hours of light delay from anyone paying attention, doing whatever it does in the dark and the cold, entirely indifferent to whether we noticed. We noticed anyway, and every time we've looked more carefully, it has quietly, patiently, without any drama of its own, revealed that we understood less than we thought. What happens next, I genuinely don't know, and I don't think anyone currently working on this problem knows either. Not the identity of the molecule sitting on 2 different world surfaces, not whether the next generation of cryogenic laboratory experiments will confirm or complicate Umahan's melting nitrogen models, not whether a future mission will ever secure the funding to return to Sputnik Planitia and watch it change in something closer to real time rather than inferred after the fact from decade-old photographs. What I do know is that the question is still open, still being chased, still being funded and argued over and refined by people who have decided, for reasons that go beyond simple career advancement, that this particular gap in human understanding is worth their working lives. Science doesn't always give us endings. Sometimes it gives us horizons, a farther edge to walk toward, visible but never quite reachable within the span of any single career, any single mission, any single instrument's operational lifetime. Pluto sits at one of those horizons now, closer than it's ever been to being understood, and further than most people realize from actually being explained. Perhaps that distance, that persistent gap between what we've seen and what we comprehend, is the point of the whole exercise, not to arrive at a final tidy answer, but to keep the question alive long enough, funded long enough, argued over carefully enough, that someone younger, more patient, or simply luckier than the researchers currently working the problem, can eventually carry it the rest of the way. We are the generation that finally flew a spacecraft past Pluto, that finally pointed a space telescope precisely enough to catch its atmosphere, behaving like nothing else in the solar system, that finally noticed liquid where liquid has no business existing. The answer, Whatever it eventually turns out to be belongs to whoever comes next.